The big result around which we build this entire section is what's known as Euler's theorem, which works in three cases for connected graphs. If you have disconnected graphs, this whole construction doesn't really work because you're not going to have a circuit or path covering the whole thing. So I put that in parentheses there to be sure we understand that that's what we're talking about, but the whole thing becomes kind of, well, arbitrarily useless if we talk about a disconnected graph. So usually when we're looking at these things, we're talking specifically about connected ones. I want to be specific in this case, but generally it's not going to be something I'll mention because, well, we need it. Otherwise it doesn't really work from the jump. Anyway, for our three cases here, we're talking about things in terms of the number of even and odd vertices that a graph has in order to have Euler, paths and or circuits. Where if we have exactly two odd vertices, that is, we have two vertices with odd degree and no more, no less, that means we have Euler paths that go between them. And I say paths plural because we can technically take one going in one direction, one going in the other direction, and then maybe any number of them in the middle there. Then if we have all even vertices, that is, every degree of every vertex is even, for example, something like a cycle graph or a circuit graph just by itself, then we will have an Euler circuit. At least one, probably quite a few of them. And finally, for our third case, if we have a graph of any other arrangement of degrees, that is, we've got exactly one with odd degree or more than two, doesn't work. In those cases, we do not have either an Euler path or an Euler circuit. We've got nothing we can work with there in terms of being able to describe these patterns. We're a very, very simple example for something that has one like this. That first case would be something that's just a path graph by itself, so that straight line construction I talked about earlier, where the ends would be the degree 1 vertices, that is the odd degree vertices, so you'd have paths running between them, you'd have the path itself, and then for something that is an Euler circuit, just think of the circuit or cycle graphs, those loops that run around some number of n vertices, where those will have Euler circuits starting from wherever you want to. You can go from anywhere to get a circuit out of that. It's a very nice and pliable construction in that way. So the next few things we're going to do here is just look at some, not necessarily basic, but direct applications of this result here. We're going to be looking at being able to identify and tell, using this theorem, where some of these circuits or paths may exist and where they may not, based entirely on the degrees of our vertices.